So on Wednesday, we reminded you of things which you may have seen before. So I hope you don't think we are or feel that we are moving too slowly. But there are some issues which are necessary when we are going to solve problems. And I wanted to remind you of some of these basic steps in what we normally call the scientific method. And if we now go back to these 4 elements. So one is to identify the system, which means what kind of object we are looking at. And I'm going to link, right after we've gone through these topics, I'm going to link that with specific examples which are relevant for the exercises in the second step. So typically you would find out which object is moving, and what kind of data you might have, how you measure positions if you have that, and so forth. That's the identify the system case. Then the next one is the one where we actually make a model. And that's where and if you look at the 2 first exercises, you actually have to identify what kind of forces are at play and what kind of system you have in order to answer the questions. So you find out which forces act on the system, and then you have to introduce models for the forces. So we have some fundamental forces, like the gravitational force, which we believe is a fundamental force in nature. There is no experimental evidence which defies that. But then we have models for the forces. And one of the models is, for instance, air resistance or friction. We do actually not have a fundamental force for that. And there we can make models. Then, when you've done that, you identify again which equations govern the system. And in this course, the thing you will see again and again and again and again is you finding the forces. And when you have the forces, you find the acceleration. And with the acceleration, you integrate up, you find the velocities and the positions. So there may be more elements which you need to define a model. When you're done with that, that's the solving part. So sometimes you can solve it analytically. And in other cases, you would have to do it numerically, which is actually the most common situation. And the exercise which you will see today, the numerical one, deals with you comparing a numerical solution to an analytical solution. And then when you're done with that, when you solve the equations, that's when you start asking yourself, what does it mean? Does it make sense? Does it agree with experiment? If you have experimental data, you evaluate the answers and implications and compare with experimental data if that's possible, and ask yourself if the model makes sense. These are the essential elements of what we normally call the scientific method. And when we are solving this with paper and pencil or numerically, we're actually solving a scientific problem with all the possible tools which we have. And that's what we want to keep doing throughout the semester when we deal with classical mechanics problems. So when you do computations, this is actually one of the tools which you would be using for solving scientific problems. So we want you in a way to think in terms of science and the scientific problem. And gradually, as we move on through the semester, the problems may become more and more involved. And one of the exercises or one of the midterms which we've been having, which everybody seemed to like, is actually to simulate the solar system. And that's a pretty fun case. And I think we should keep that because it's a fun problem. Okay, so let's, I may take down my mask because I think it's a little bit strange to speak. So I hope you don't mind if I keep it a little bit down and I'm just staying in the corner here, if that's okay. So the Newton's laws are those which we essentially deal with. And we discussed some of these topics yesterday. So we need to divide the problem into system and environment. We should make a figure and everything in contact with the object. We find the contact points, give names and symbols to all the forces, identify long-range forces, then you make a drawing, and then we find a coordinate system. And that's the system which we will typically use to solve the problem. So let's take a quick look at one of the typical cases which we are going to encounter. So let's look at one of the first cases which we looked at was that of a falling object. So if we want now to apply this, and if you look into the exercise set which we have this week, you will see that there are pretty similar cases to that. So we have a falling object, and then we have to identify the forces. So the falling object is our system. And clearly, one of the forces which is at play is the gravitational force, which we just marked like that. We've chosen a coordinate system. And in this specific case, if we now plot this in 3 dimensions, for this specific problem of an object which falls just vertically, there is no point in setting up a 3-dimensional problem. That is what we would call an overkill, right? So for this specific case, we can just stay in 1 dimension. And as I said, I really thrive in 1 dimension. When I get into 2 and 3 dimension, I'm getting a little bit on shaky grounds here. So we would simply say now that we keep the y-axis. So this is our degree of freedom, y. And then we could add now, when we are modeling this system, we could think of adding a air resistance force, which is normally called a drag force. So we could now think that there is a force which acts in the opposite direction. And I'm just going to call this for FOD. So in some of the first exercises, this is exactly what you're going to do. Next week, we are going to look at this problem in 2 dimensions. So we are going to give the system a velocity in the x direction and a velocity in the y direction. But now we're just thinking that acceleration goes down in the y direction only. So if we now identify the forces, what we would say now is that the net force, so let's keep arrows on top of the quantities. So we have the net force, that would be this drag force, plus the acceleration here, the acceleration, the gravity force. Now, we know the expression for that one. So this would be equal to minus n times g. And since this is now acting only in the y direction, we can put now a vector symbol, a j, to indicate that this is just going in the y direction. Now, this drag force is also a force which we now assume acts only in the y direction. This is just a simplification. So the example you will look at a little bit later now in the numerical exercise, we are going to assume that the system can move in the x, y, and z direction. But here, we would now have an f, and we're going to call this dy component. And this is also multiplied with j here. Now the gravitational force is a fundamental force. The drag force is something which we don't have an analytical expression for. And this is something we will need to make a model of. So a typical force which you might see here is actually something which is proportional with the velocity squared. So this f dy could now be given by a constant, which we call d. It's normally called a drag constant. And then we would have the velocity squared multiplied with this unit vector minus m times g times the unit vector in the j direction. Now, since we are just in 1 direction, it's a 1-dimensional system, we would normally skip these unit vectors. We don't need them, right? So in general, this drag force, if the object is moving fast, this is normally given by a minus d times the velocity vector multiplied with the absolute value of the velocity. If it moves slowly, then it's normally proportional just to the velocity. So this is a fast moving object. And if it's slow, what we would have then is something like a minus. And now we're going to give this a new constant, k. And then it may just depend on the velocity. So this is a slow moving object in, let's say, a fluid, or it could be in air, or some kind of medium which it is moving in. So these are models which we make. And then clearly, if you have data for the positions of the object, you can perform the calculation, and then you can compare the model which you have come up with data. And that's the common approach in the scientific process. So you have some fundamental forces. The gravitational force is one of them. This is a long-range force. And then we have what we might call short-range or contact forces, of which this air resistance or fluid resistance is an element of. So normally what we would do then, if we go in 2 dimensions, depending on the initial conditions, so suppose we move into 2 dimensions, and then we take the x and the y direction, then we would still have the gravitational force, which would simply be given by m times g times j. So this is just acting down towards the Earth, and we decide that that is the j direction or the y direction. But then this object could have an initial velocity, so that's moving in the x and the y direction. So that means that this gravitation or this drag force, Fd, that could now have a component which we would call Fd of x times I plus Fd of y times j. So in our case, if we have an object which moves fast, an example of this could be the following. So it would be v, and that would be this constant minus d, and then I would have the velocity in the x direction times I, multiplied with the absolute value of the velocity, minus d times v, the velocity in the y direction, times j. So these are the vectors, and multiplied with v. So this is the absolute value of the velocity. So this is a typical case which we will encounter. And then clearly you can make it more sophisticated. You can add a 3rd dimension if that is needed. So physics, keep this in mind, physics is about finding the relevant degrees of freedom. So if an object is just falling down, there is no point in running the calculations in 2 or 3 dimensions. Then you can simplify the problem to 1 dimension. If you have a velocity in the x and the y direction, then obviously you would stay with 2 dimensions, if that represents the relevant degrees of freedom. So next week, in one of the exercises, you're actually going to see an example of where, 1, you don't have an analytical solution, and we are going to deal with an air resistance in the x and the y direction, which depends on just the velocity, not the velocity squared. So let's look at the case with the velocity squared, because that's a case which we can solve analytically. So let's quickly bring that up before we move on to the exercise solution. So let's go back now to 1 dimension. So only 1 dim. In this case, we don't need the vectors because that's a redundant quantity. We're just falling in the y direction. So in this specific case, the net force on the system, and now I'm skipping the vector signs, would be given by minus d times v squared. And then I would have minus. So actually now I have to be a little bit careful because this force is going upward. So that means I have to have a plus here. So it's opposite because the object is falling down. So I'm looking at the velocity in the negative y direction. And that's because the object is falling down. So then I have minus m times g here. So this defines now my acceleration, because this is going to be equal to m times a. And now I can reshuffle the equations a little bit, because I know that this is equal to m times dv dt. And then I get plus dv squared minus m times g. So recall now that when I looked at this force here, this drag force, I wrote this in terms of a vector here. And normally it's opposite. the motion you have. So it comes with a minus sign. But since the object is falling down, this force acts in the opposite direction. And that's why it gets a plus sign, because the velocity goes the opposite way. If we are looking at the velocity going down, you can think of that as a negative direction. And that's why you get a plus here. Okay, so the equations you get then, you can now divide by m on both sides. So we take a divide with that one and divide it over here with m. So what we would get then is just an equation which runs like dv dt is equal d divided by m times v squared minus g. Now the trick, as we did without the drag force, is simply to take this equation here and multiply with dt on both sides, so that we can isolate on the right-hand side, we can isolate time, and on the left-hand side, we just isolate velocity. So if you do that, we can rewrite this equation in the following way. So I can have a dv divided by, and now I'm just going to call this a new constant. So I'm going to call this for a d tilde, which now contains the mass of v squared minus g, and this is equal to dt. This is something which I now can integrate up. So typically, we would now have a final time, t final, which I'm simply going to call for t. And I'm going to have a t initial, which we call for t0. And we simply set that one to 0. Remember now that we can choose the initial conditions as we want. I'm going to define a v final, which I just call for a v here. And then I have a v initial, which I call for v0. And we're just going to set that one equal to 0 meters per second. Now I can integrate up. So I integrate up the left-hand side, v here. Now I need to have a prime quantity because it's not the same as the final result. There's a d, and then I have a v prime minus g, and that's equal to an integral from 0 up to t over dt prime, and that is obviously equal to t. Now, the integral which you see here now, with these specific initial conditions, that's something which we can solve analytically. And that's going to give us a tan hyperbolicus function. And I'm going to just go, so this is something you would typically look up in a mathematical table. So I just wanted to show you the final answer, which you will find in the lecture slides. And next week, we are going to start with similar problems, but we're going to look at a problem in just 2 dimensions, but where the velocity now, or the drag force, depends only on the velocity. And in that case, we will not be able to find an analytical solution. The thing, however, which is extremely useful with this one, is that you can compare an analytical solution to your numerical results. And that allows you to build confidence that what you're doing is correct. So let me go back to the slides. So let's do that. And then we are going to stop after that. And then we are going to look at the exercises. So if you look at this problem, you will actually find this problem in the notes here. This is what we did last week. So this is just for the sake of completeness. Now, what we do now is that we have a force like this. So this is what we defined. And this integral, which we are looking at, this one is actually given by inverse tan hyperbolicus. So when you integrate up, then you take the inverse of the tan hyperbolicus, and you can find then that the velocity is given by this equation here. So I invite you to take a look at it. The kind of things which we are going to do in the exercises and so on are going to be similar to this. So sometimes we can find an analytical solutions, and sometimes we are not lucky, and we have to do it numerically. Next week, next Monday, we will discuss a little bit about the numerical solution, but we're also going to discuss a little bit more about forces and other properties of forces like conservation laws and so on, which are going to be important for us when we solve physics problems. So when you have that equation, you can actually then integrate this up again. And if you integrate up again, you can then find, and this is a little bit more trickier integral, but you can find it in tables of mathematical formula. And what you would see then is that you get this uglier equation with a cosine hyperbolicus and a log. So it took me some time to remind myself about integration. And I guess this is not what you will be asked about. So this course is not about tricks in finding such solutions. We are interested in understanding what is the physics behind the solution. What does it mean to us? And if you now have a force model for the drag force, this air resistance, you can then, if you make a measurement, you can then compare your numerical simulations with a measurement. And then you can say, hey, perhaps this drag force is meaningful or makes sense if it runs like v squared. If it defies what you get numerically and also by paper and pencil, it may mean that you have to go back to your drawing board and find a better model. And then you would go back and forth till you get a decent agreement with experiment. So one thing which may surprise you, actually friction, air resistance, and all these things, that's a huge area of research. And it's extremely important in, for instance, a field like material science. So if you have two objects sliding on top of each other, you want to understand what is the friction and what causes the friction. And to develop models for that is actually a pretty hot research area in material science. And we don't have a fundamental law for it. And that's interesting because that means that there's much more for us to do actually. So I'm going to stop the recording here now. And we are going back to the exercises for this week. So let me just pause the recording.